So the primary thing that we're going to study and be interested in this course is the stress in the earth. So I'm going to use the word stress not in a mathematical way today. I think most of you have a concept of stress, right? It's basically force acting over some area, okay? But I think just also very colloquially, we all know what stress is, right, to some extent. And so when we talk about tectonic stresses, these are the stresses that are naturally occurring in the earth, okay? And we'll talk about why they occur a little bit, and then we'll try to figure out ways in which they affect petroleum engineering. Why do we care about these naturally occurring stresses? And today we'll kind of focus on tectonic stresses, but there are also other ways, other than just to say the movement of the earth, that stress can develop in the earth, and we'll get to those as we go. Okay, so why is stress important in petroleum engineering? And there's a lot of reasons, but we'll kind of go through a couple examples at least that we'll talk about in more detail later in the class. One of the ones we'll spend quite a bit of time on this class is with respect to well bores and drilling. Okay, so well bore failure occurs because there's the stress naturally in the rock exceeds the strength of the rock. And rocks also have different strengths in tension and compression, of course. Most rocks are actually quite strong in compression and very weak in tension. So it's not just the magnitude of stress, because as we'll learn next time, and as you probably know, stress is actually a tensor, right? So if you don't know what that is, don't worry. We'll cover it. But there's more than one value for stress, and so the actual stress, the full state of stress, the stress tensor, is what really matters, because when we design well bores, especially in deviated wells and other things, if we don't have the correct state of stress or hoop stress along the well bore, then we can get tensile failures or other types of failures, and then you have an unstable well bore. Okay, so this is one aspect of why we care about stress as petroleum engineers. Another one is related to faults, and so here I've drawn or used a picture of a very large, geologic fault, but these could be much smaller joint sets or faults that you'd find in a reservoir as well, and these faults or joints will slip according to the amount of force and friction that's along the walls, okay? And this can be a good thing sometimes in the case of stimulating tight reservoirs, like in the case of slickwater fracking, but it can be a very bad thing in the case of induced seismicity, where we're injecting wastewater from hydraulic fracturing operations and causing small earthquakes, right? It's something we prefer not to do because it doesn't make the public happy. Another way that stress is important is in the reservoir depletion. So as we drain a reservoir, and this is sort of the other aspect of stress, is the actual pore pressure. So most rocks, certainly the ones we care about, are saturated with oil, natural gas, condensate, water, other things, right? And as we drain that fluid out, we're basically depleting the pore pressure as well, which sort of affects the overall stress in the material. And that can be a good thing, and it can be a bad thing. And so this is intended to, this is a commercial simulator that actually simulates the effect of reservoir depletion on the stress state. And so what you can actually get is subsidence. So as the fluid is drained out, then the stress is relaxed, and the rock is effectively not as strong, and the earth will actually settle right there. And that can be a good thing, and it can be a bad thing. You can actually measure this subsidence from the surface. It can be that significant. Okay, so we'll talk a little bit about where these tectonic stresses come from. And I think just from the word tectonic, you know that it comes from, or partially comes from, the movement of the plates and faulting and other things, right? And so this is really high school stuff. You probably learned in your high school geology course, but the Earth is, of course, not solid. There's a very, very thin crust, a large mantle. This is a melted region of magma, right? It's a kind of a mixture of solid and liquid material. More solid near the top, more liquid near the center, and then a solid, you know, basically iron core. Okay, and it's actually the movement of the magma around the core that causes the electric, you know, the polar field on the Earth. Does anyone have an idea how we know that there's a large, you know, that there's a large liquid region in the middle of the Earth, other than the fact that, I mean, certainly in some areas you see the activity in volcanic activity and otherwise, but say in an area far away from any volcano, how do you actually know that what's deep under there? Exactly. Yeah. So you have pressure waves and shear waves, and we can resolve those. And if you propagate a shear wave into the Earth, a shear wave doesn't propagate through a fluid, so we know that. So this is sort of a schematic to kind of get more detail into what's going on kind of up here in the so-called lithosphere. So the lithosphere includes the crust and the uppermost mantle. So the uppermost mantle has some solid material in it as well. And just to give you an idea of the scope, so the crust is, you know, anywhere in this picture they say from 0 to 100 kilometers thick, but it turns out under the ocean, the oceanic crust is much thinner than that. In some places as thin as maybe 4 kilometers. So somewhere under the ocean, it's typically on the order of like 4 to say 50 kilometers, and then in the interiors of the continents, it can be very deep, you know, up to like 100 kilometers deep. And the overall, say, aerial density of the crust is roughly the same. So how could that be? I mean, how can, if I'm telling you the density is the same, yet it's so much thinner over the oceans and so much thicker over the continents, why do you think that is? It's the composition of the rock. So the ocean rock is mostly of a basaltic type nature, and the rock over the continents are more granite type, which includes a lot of quartz and other things that are much lighter. Okay, so it's the Earth's way, the thickness of the crust is sort of the Earth's way of keeping everything in balance. So somewhere in the early 1900s, I think like 1912, there was this theory proposed of continental drift. So, and this is sort of the precursor to the more modern theory of plate tectonics, which came around in the 60s, and you know, it's basically what we believe to be true today. So the idea of continental drift is that, and it wasn't necessarily wrong, it's just not complete. Is that this idea that, you know, all the continents used to be one supercontinent called Pangaea, and over time they began to move away from each other. And of course, as we move along into, you know, say the Jurassic and Cretaceous periods, when our friends the dinosaurs were around, the fossil records sort of let us know that are in agreement with this idea. In other words, we find fossils that are common to the regions where the continents used to be tied together. And, you know, so there's when our dinosaur friends went extinct, and then today what we have. Okay, so the incompleteness was to the understanding, and you know, I don't know enough about the literature to say that people actually believe that, say, the continents floated on the ocean. I don't think no one believed that, but there was it wasn't really well understood why the continents moved around until this kind of idea of plate tectonics in the 60s, and a lot of it is also because what we see when it comes to tectonic plates is mostly they are, you know, invisible when we're standing on Earth. And one reason that things became a little more solidified in the 60s was because we had satellites and we could image from high in the sky, and there we can actually resolve several of the faults that occur along tectonic plates. So this idea of plate tectonics is there are large, massive lithospheric plates, so they include the crust and the lithosphere, the crust in the upper part of the mantle, and you'll also hear them called lithospheric plates sometimes. And this idea that they slowly move around, and we'll talk about the reasons that they're moving in a second, but they move around and tend to, you know, generate new material in some areas, and then that pushes the plates underneath each other, and they're always evolving. In fact, it's maybe a little bit hard to see in this picture, but this Juan de Fuca plate, which is right on the coast of Oregon and Washington, basically, is disappearing. So it's going underneath the Pacific plate. So typically the oceanic plates will move because of their thin and density. They'll move underneath the continental plates, which are lighter. And at some point in our future, you know, another 50 million years into the future, if humans are still on this planet, we may move to a different planet by then. But at some point in the future, we'll see that Juan de Fuca plate is completely gone. Okay. So the size of the Earth and the size of the crust of the Earth has roughly been the same throughout Earth's 4.5 billion years existence. So whenever a plate like that subsides underneath another one and appears to disappear, there's new material being generated from you know, volcanic activity, essentially. So along the plate boundaries, we have different types of plate boundaries. The one that sort of regenerates the material are these convergent plate boundaries. So these, and here's a picture where you have an ocean ridge, and you know, basically magma is coming into the ocean and being cooled, and this pushes the plates on either side of it away, and hence the word, I'm sorry, this is divergent. Try that again. So we're talking about a divergent plate. It's the one where magma is coming in and pushing the plates apart. Okay. Convergent plate is where two plates are coming together. Okay, and then you typically have one plate subducting under the other. So that's if you can't read that, that's subduction. And so this plate is moving underneath the other one, and this often occurs again with oceanic plates where there's a convergent plate in the ocean, basically generating new material, pushing the plates apart, and then because of the thin nature of the oceanic crust and the fact that it's less dense, it'll be pushed under the continental shelves and create faults. Okay. The other type is a transform plate boundary. So in transform plate boundaries, basically due to the nature that you have material being pushed away. You have material being pushed away here, and while it's subducting here, it's being resisted by friction, of course, right? It's very hard for those plates to be subducted. So kind of in the interior, you have these transform plates, and these are basically areas of shear and lots of cracking. And in fact, lots of cracking, large fractures. Okay, so these are large fractures, and most of these occur in oceans. But we have a very important one on our western coast that everyone knows, which is San Andreas Fault. So the San Andreas Fault is of this type, a convergent plate boundary. I mean, a transform plate boundary. Okay. So the reason we really care as far as plate tectonics go is because the plate tectonics then cause faults, and these faults are a major source of stress, and we'll learn about how to resolve stress on these faults in this course. Okay, so just here we'll visually characterize the types of faults, and then later we'll talk about the characterization or classification due to the nature of stress on the fault after we learn about stress. So a normal fault is described in this picture, where you always have sort of the footwall is always the side of the fault in which goes into the incline. And the reason it's called a normal fault is, if you could imagine that this picture as I have it drawn is floating in space. If I fix the footwall, okay, and then I apply gravity, which side is the hanging wall going to, which direction is the hanging wall going to move? Right? Normal to gravity. Okay, that's why they're characterized as a normal fault. Okay. So sort of the opposite of a normal fault is a result fault, is a reverse fault, and the same idea. If this were floating in space, and I fix the footwall, and then I apply gravity, but I apply it in the reverse direction. Which way is the hanging wall move? Right? So that's why, just think, if you can just remember that, right? This normal gravity, reverse gravity. Which way is the hanging wall going to move under those conditions? And that's how you characterize the two faults. Okay. The other type is a strike-slip fault. So this is where two faults come together and slide. That one is pretty easy to think about. This is also what the San Andreas fault is, and what most transform faults are. Okay. So the reality is, though, that real life is much more complicated, and real faults don't exactly look like these idealizations. Real faults can have many of the characteristics of several of these. And in fact, like I said, the San Andreas fault is about 95% strike-slip, but also has some normal faulting activity as well. Okay. So then the sources of tectonic stress are these plate driving stresses that are due to the motion of the tectonic plates. Okay. And again, they can be caused by the plates being pushed by compressive forces from these mid-ocean ridges. Of course, the mantle is molten, but there's some solid material in there, especially near the top, such that when the plates slide over it, there is friction. Okay, there is friction there, and that can cause additional stress. And of course, a very large one is the frictional resistance due to subduction. So just like I said when I had the picture up early, as one plate slides under another, that's very difficult to do. There's lots of friction there that compresses the plate itself and causes these tectonic stresses. Okay. So there's also buoyancy forces, so density anomalies, right? So while I said that at the beginning the density of the crust is roughly the same, it's obviously not completely homogeneous. It's not completely the same everywhere, right? And if you had, due to the nature of the material in the crustal region, you could have a lot of, say, dense materials that surround a very not dense set of materials, and that density difference itself, combined with gravity, would cause additional stress in the Earth. Okay, so everyone sort of know what I mean by that, right? So, and of course, also, you can have density anomalies due to plate thinning and thickening due to stress itself. So the stress state affects the stress state, right? So you're pulling on the plate, or the plate is being compressed, and it gets thicker, and therefore it becomes more dense because it is a compressible material, becomes more dense, and then gravity, the body force of gravity, acts on that dense material in a different way, and that can cause additional stress. Okay, and you can also have plate flexure. So you can have just simply sediment loading, just simply the earth piling on top of itself can cause the plates to flex, and these flexures can be very, very big. So I give an example here that the wavelength, or the the kind of characteristic arc of the flex can be very large, like 1,000 kilometers. Okay, so these are this sort of, like I said, it was a very short lecture. This concludes that, and next time we'll actually get into sort of the mathematical definition of stress, and then once we have that, we can talk about other things that affect the stress, like the pore pressure and other things. Okay, so I'll see you Thursday.